surface preparation methods are usually dictated by the suitability of the electrode for. There are four options. First one, observing an electrochemical parameter such as heterogeneous electron transfer rate, observing an electrochemical parameter such as redox potential, observing an electrochemical parameter such as surface coverage, and fourth one, all of the above are correct. So as per the study, so if I go for the answer this question, the choice of the electrode material is basically in various applications are usually detected by the suitability of the electrodes for specific purposes or functions. The suitability is determined by the requirement of the application and the characteristics needed for optimal performance. Here are some common factors that influence the choice of electrode material and surface preparation method. So there are four. The first factor is the electrochemical reaction. So the electrodes are often used in electrochemical processes where the choice of the material depends on its ability to catalyze or facilitate specific electrochemical reactions. That means the basically for the electrochemical process, the choice of electrodes are depend on how this electrode help to catalyze the reaction. So for example, in fuel cell or batteries, the electrode material should promote efficient redox reaction. The next is the corrosion resistance. So some application involve exposure to the corrosive environment. The electrode material need to be corrosion resistant to maintain its structural integrity and functionality over time. It means basically in some cases for electrochemical application, the electrodes are placed in a very harsh environment or in a very oxidizing condition, which decreases the performance of the electrochemical cells by corroding the electrode. So in this case, we need to be careful about their for this type of case, we need to be careful for choosing the electrode material. Now moving to the third one, that is conductivity. The electrical conductivity of the electrode material is crucial, especially in application where low resistance and efficient electron transfer are essential. Metals with high conductivity such as platinum or graphite are majorly chosen. So the conductivity of the electrodes. So for electrochemical cell, the electrode material which are chosen are usually should be electrically conductive, or they can conduct electricity. So and certain cases where low resistance and efficient electron transfer are essential, metal with high conductivity such as platinum or graphite are majorly chosen. So there are first 3 points is the electrochemical reaction, corrosion resistance and conductivity. Now moving to the fourth factor. The fourth factor is the biocompatibility. For biomedical application, electrode may come in contact with biological tissues. Biocompatible materials such as certain metals or conductive polymers are chosen to minimize adverse reaction and ensure compatibility with the biological systems. So here comes the fourth factor, that is biocompatibility. Now moving to the fifth factor, temperature stability. Some application involves high temperature or extreme temperature variations. The electrode material should have good stability under these conditions to maintain the performance. Surface area and porosity. The sixth factor is the surface area and okay, so I'll give an example of that. Fifth, there is a temperature stability. The temperature stability in the case of high temperature fuel cell or high temperature solid oxide fuel cell, the electrode material need to be stable at high temperature. So for this case, in that case the electrode should be chosen which can sustain at high temperature without degrading its performance. Now moving to the sixth question. The sixth question is the surface area and porosity. The surface area and porosity of an electrode are also can impact the effectiveness in processes such as electrochemical sensing as well as catalysis. If the surface area is increased, it enhances the contact between the electrode and the surrounding environment. The next one is the mechanical strength. Mechanical strength is an important in application where electrode may undergo physical stress such as structural application or when an electrode is used in a harsh environment. So mechanical strength is also another important factor for the application where in that cases when electrode can usually undergo a physical stress. Number 8 is the surface wettability. Surface preparation methods are chosen to modify the wettability of the electrode surface. This is crucial in application where liquid gas interface plays a role, such as sensor and electrolyzer. Suppose sensing in water matrix or in the wastewater treatment process, the wettability of the electrode material plays an important role, which helps the pollutant to getting a most contact to the electrode and help to understand its quantity. So next is the adhesion and bonding. Surface preparation methods are also consider the adhesion and bonding of the material to the electrode surface. Sometimes they are required to adhere suppose in the case of solid oxide fuel cell, I may say the surface preparation play a vital role to attach the electrode material with one another along with and also with the uh, electrolytes. Now the 10th one is the cost and availability. Practical considerations such as cost of the material and their availability plays a role in the selection process, especially in large scale or commercial application. The last one is the catalytic activity. In application where catalysis involved, the electrode materials catalytic activity is a significant factor. Certain materials like platinum are known for their catalytic properties. So based on this, so as I say, if I strongly point out one by one, so there are basically 11 factors. One, electrochemical reaction, corrosion resistance, conductivity, biocompatibility, temperature stability, surface area porosity, mechanical strength, surface wettability, adhesion, bonding, cost and availability, and catalytic activity. So based on this we can stay. So if I go for by keeping in this thing in mind, there are 4 options as we saw. The observing electrode such as heterogeneous electron transfer rate, redox potential, surface coverage, and all of the above. So the correct answer of this question is all of the above. Now moving to the next question. Despite its black color as a bulk sample, thin film of disordered graphitic carbons are partially transparent in the far red wavelength range, partially transparent in the visible wavelength range, or completely transparent, partially transparent in the UV wavelength range. So, basically, graphite carbon is a type of carbon-based material. It's a basically we can say it's a graphite carbon somehow relevant, or graphenes is somehow relevant to the 2D carbon nanomaterial. So the thin film of disordered graphite carbon may appear black at macroscopic level, but when the film thickness is in order of the wavelength of the visible light, that is 100 of nanometers or less. So there are several factors. If I go for the wavelength, electromagnetic range of wavelength, so we can find there are various factors which play a significant role. So there are various factors. So I'll share you the electromagnetic wavelength, the diagram of the electromagnetic wavelength. Just a minute. So if I say there are 7 types or 6 types. So first it comes as gamma ray, which has the less one. The value of gamma rays is around like it in angstrom or 0.0001, or we can say it's in the range of 10 to the power minus 12 meter. 10 to the power minus 12. Then it comes the X-ray. X-ray is in the range of 10 to the power minus 10, 10 to the power minus 10. Next come is the UV ray. A third is the come is UV ray. UV. So the UV range is comes around 10 to the power minus 8. The next cup is the visible range. Visible range is in the range of around 4 into 10 to the power minus 7. Now moving to the next one, that is infrared or IR red. IR is in the range of in the range of 10 to the power minus 4, 10 to the power minus 4. Then comes the microwave. Microwave comes around 10 to the power minus 2. then comes as finally the radio wave. Radio is a 10 and 10 square. So this is the electromagnetic spectrum. So as I say, the thin film or the disordered graphitic carbon may appear black at a microscopy level, but when the film thickness in the range of the wavelength of visible light length, like around 400 to 700 nanometers or even less, they can exhibit the interference effect. This interference can lead to changes in the appearance of the thin film and making it partially transparent or showing interference color. So now we'll go to the next important concept I will discuss, that is the interference. What is the interference effect? So just a minute. Okay. So the next question comes as the interference effect. So I will show a diagram of interference effect. Okay. So interference is basically the overlapping of the two wavelengths one upon another is known as the interference effect. So suppose it's a light source. So suppose this is a source, and this is two slits. So from source we got, so this is the source, this is a slit. So suppose two mirrors are placed, so from the source it started to reflect on the mirror, and from mirror we get two wavelengths and they coincide or overlapped at a certain point. So this after that they will get a single kind of wavelength. So this is known as interference. So I'll give you a more clear picture one more time. So this is the source, this is two graphs. So one light is given here, one source is given here, then we can go for the it reflected and emit a certain point and we give a certain wavelength. So this is known as the interfering effect, when two waves are coincide or overlapped each other. So interference can be of different type. There are basically two type. One is the constructive, one is the destructive. So I'll give one more a small example of the constructive and destructive. Okay. So suppose for constructive there are two wavelengths. First one is this one and second one is also this one, and when they two meets, the constructive wavelength is like this one. This is the constructive one, and the destructive one on the same cases, when the wavelength is it enhances the frequency or peak height, and in the case of destructive it become a straight line. That is a destructive interference. So it can exhibit the interference effect. This interference can lead to the changes in the appearance of the thin film, making it partially transparent or showing interference colors. In this case, the disordered graphitic carbon, the thin film may exhibit transparency or coloration based on their thickness and the interference effect. This property is exploited in various applications such as anti-reflective coatings, optical filters, and coating for electronic devices. The optical properties of the thin film can be influenced by factors like degree of disorder in the graphitic structure, the film deposition method, the specific condition during the film formation. Thin films of disordered graphitic carbons have application in optics, electronics, and in material science due to their unique optical characteristics. Now moving to the next question. So as per this question, we can say the black color as a black sample thin film of disordered graphitic carbons are the partially transparent in the visible wavelength range. Now moving to the next question. Following substrates are of key importance for most practical thin film devices. There are 4 options. First one is the platinum, carbon, silicon or glasses, all of the above, and gold. First of all, platinum. Platinum is often used as a substrate for various thin film devices, particularly in applications where stable and conductive surface is required. It is commonly used for the fabrication of sensors, electrodes, and certain electronic devices. So basically, platinum is often used as a substrate for various thin film devices, and basically where in this case the basic property of platinum is where in the application require a stable and conductive surface, and basically used for sensors, electrodes, and certain electronic devices. The next one is the carbon. The carbon-based substrate such as glossy carbon or other carbon material are used in certain thin film devices, especially those involving carbon-based thin films. Carbon substrates are commonly used in electrochemical applications, biosensor, and some electronic devices. So carbon-based substrates such as glassy carbon or other carbon material are used in certain thin film devices, especially those involve carbon-based thin films. So the commonly used carbon-based substrate are glassy carbons, and they are used in thin film substrate for electrochemical, basically in the case of biosensor and electronic devices. Now moving to the question number 3, that is silicon. So silicon is widely used substrate in the semiconductor industry. It is a fundamental material for the fabrication of integrated circuits and microelectronic devices. Silicon wafers are commonly used as a substrate for thin film deposition in a process like CFD, or that is chemical vapor deposition, and physical vapor deposition. So silicon is most commonly used in semiconductor industry, and they are majorly used for the fabrication of thin film for the deposition of thin film and the fabrication of integrated circuit and microelectrode devices. The fourth option is the gold. Gold is often used as a substrate for this thin film in the application that requires good electrical conductivity as well as corrosion resistance. It is commonly used in electronic devices, sensor, and in some cases as a reflective layer in optics. So gold has a property which shows its corrosion resistance behavior, and it is majorly used in electronic devices, sensor, as well as in various reflective layer in optics. So based on the question, that the key importance of most practical thin film devices, the following steps. So following steps are of importance. Which of the correct answer is gold. All of the above and gold. Now moving to the next question. The next question is cyclic voltammetry is an electrochemical technique which measures. So first, there are four options. The current that develops in an electrochemical cell under condition where voltage is in excess of the predicted by the Nernst equation. The voltage that develops in an electrochemical cell under condition where current is in excess of that predicted by the Nernst equation. The voltage and current simultaneously measures impedance of the system. So the cyclic voltammetry or CV, it's an electrochemical technique which measures the current response of an electrochemical cell as a function of an applied potential. So basically it's a normal graph. It's provide a graph where we always get the graph of V versus I. So it responses the current based on the function of a applied potential. So the current is, so here the current is basically, so the current is basically the function of V. So these techniques provide valuable information about the redox processes occurring in the system under investigation. It helps, it's basically done, cyclic voltammetry is basically used for measuring the redox processes. So in a typical cyclic voltammetry experiment, the applied potential is varied in a cyclic manner and the resulting current is measured. So this is the diagram of a black box of a cyclic voltammetry. So setup, so there are three electrodes that are majorly that should be present in a cyclic voltammetry. The first one is the working electrode, the second one is the reference electrode, and the third one is the counter or auxiliary electrode. So the working electrode is the electrode where redox reaction take place. It basically application when we do in the laboratory. The working electrode is our the material we are going to test. The second one is the reference electrode. It defines the zero potential for the cell. It is usually made of AgCl. And the third electrode is the counter or auxiliary electrode. It needed to complete the circuit. Usually it is made of platinum wire. Now moving to the next question. So as I mentioned in the last part only, the typical voltammetry setup involves the presence of with three main components. So one is working electrode, reference electrode, and counter electrode. So the next one is the potential sweep. The potential applied to the working electrode, it swept continuously in a linear or triangular waveform. The potential sweep is typically performed from a starting potential through a specific potential range and back to the starting potential. Okay, so if I see a voltagram, if I draw a voltagram, I can able to explain it more properly. So in this case, so this is the I and this is the V. This is the V and this is the I. Sorry for the mistake. This is the I and this is the V. So first we will increase the voltage after a certain point and then reaches to the initial, and again then from here to here, and after reaching to the voltage to this particular point, again the sweep back and the voltage going in a reverse direction and we get a current in a reverse direction. So the basically one is from forward direction and the voltage other case in a backward direction. So first in the case to understand the potential sweep, we can say in that three electrode system will provide the voltage. We first increases the voltage after a certain point, and after that point we started to decrease the voltage and get back to its initial values. So the third point is the current measurement. As the potential is swept, the current flowing through the electrochemical cell is measured. The working electrode experiences oxidation and reduction reaction, which is changes in current flow. So basically, as the potential is swept, the current flowing through the electrochemical cell is measured. The working electrode oxidation and reduction reaction leading to changes in the current flow. The fourth option is the redox reaction. During the forward scan, the potential is increased and leading to the oxidation reaction at the working electrode. Oxidized species are generated and electrons are released. And during the reverse scan, the potential is decreased, promoted reduction reactions. Reduced species are formed as the electrons are accepted. So basically, during the forward scan, the potential is increased and leading to the oxidation reaction at the working electrode, and because of that, the oxidized species are generated and the electrons are released in the system. Whereas during the reverse scan, the potential is decreased and the reduced species are formed by when the electrons are accepted by these electrodes. Now moving to the fifth part, that is the cyclic voltagram. The resulting graph like this one is known as cyclic voltagram. It plots the y-axis as an applied potential over the course of potential sweep, and the cyclic voltagram is typically contain the characteristics peaks as well as the characteristic drops. And if I go for the peak analysis, as I say, the peaks of the cyclic voltagram corresponds to the oxidation and the reduction process. The position of the peak on the potential axis provided the information about the redox potential of the system. And the seventh point, the shape and width of the peak can indicate the reversibility of the redox reaction. If we get a very well defined symmetric peak such as like that, so we can say it's a reversible reaction. if I get a broader or asymmetric peak, something like this. So we can say in this case it indicates the reversibility. So there are 7 major parts. One is setup, potential sweep, current measurement, redox reaction, cyclic voltagram, peak analysis, and peak shape and width. So based on this case, we can say the cyclic voltammetry is an electrochemical technique which measures the current that develops in an electrochemical cell under condition where voltage is in excess of that predicted by the Nernst equation. Now moving to the next part. Carbon electrodes are commonly used for what? So there are 4 options. One is the metal production, energy storage in batteries and supercapacitor, catalyst support, and all of the above 3 choices. So one of the most common used carbon electrode, as I mentioned earlier, is the classic carbon. So carbon electrodes are commonly used for variety of electrochemical application due to their unique properties. So the first application is the batteries and energy storage. So carbon based materials include carbon electrodes are widely used in batteries. They can serve as anodes as well as cathodes in different types of batteries such as lithium ion batteries, supercapacitors, and fuels. Now moving to the next part, that is the electrochemical sensor. So the electrochemical sensors, basically the carbon electrodes are commonly used in the fabrications of electrochemical sensors. So the sensor can be designed to detect specific analyte or substances such as pollutant, microbes, or any other analyte. So making it valuable for environmental monitoring, diagnostics, as well as in industrial application. The third point is the electrolysis. In electrolysis process, carbon electrodes are often employed to facilitate the electrochemical reaction that lead to the decomposition of compound into their constituent elements. For example, carbon electrodes are used in the production of chlorine and aluminum through electrolysis. So basically, the electrolysis process, carbon electrodes are majorly used. It's help to decompose the compound into their constituent elements. Carbon electrodes are used to producing chlorine and aluminum through catalysis. So carbon electrode helps also help in catalysis process. The fourth one is the electroplating. Carbon electrode can be used in electroplating processes where metal is deposited onto a conductive surface. The carbon electrode facilitates the necessary electrochemical reaction for the metal deposition. So carbon electrodes can also be used in electroplating processes where a metal is deposited onto a conductive surface and the carbon electrode facilitates the necessary electrochemical reaction for metal deposition. Now moving to the next question. The first part is the corrosion studies. Carbon electrodes are utilized in electrochemical corrosion studies as well to investigate the corrosion behavior of different materials. So it also can be used to understand the corrosion behavior of different material. The electron can stimulate a condition of corrosion aids corrosion and aid in understanding and preventing corrosion processes. So the sixth part is the supercapacitor. So carbon based material included activated carbon, graphene, carbon nanotube are commonly used for the electrode in supercapacitors. This device stores electrical energy through electrostatic separation of charges at the carbon electrolyte interface. The seventh one is the fuel cell. Carbon materials are also used as an electrode in fuel cell which convert chemical energy directly into electrical energies. Carbon-based electrodes such as porous carbon supported catalysts play a role in electrochemical reaction within the fuel cell. Number 8 is the water treatment. Carbon electrode can also be applied in electrochemical water treatment processes where electrochemical reaction help to remove the pollutant and contaminants from the water. This includes application like electrocoagulation and electrochemical oxidation. And the number 9 is neuroscience and biosensing. Carbon electrode, especially those made of glassy carbon, are widely used in neuroscience research and biosensing application. They are employed in recording the electrons in a electrophysiological experiment to measure the neural signals. So carbon electrodes are commonly used for metal production, right? So metal production, we can say it is a part of electroplating process which help metals are deposited on the conductive surface. Energy storage in batteries and supercapacitor, that I already told. Catalyst supports, yeah, it can also help in remove the wastewater treatment as well as in electrocatalysis process. So we can say all of the three choices are correct. Now moving to the next question. What is the significance of varying the scan rate in cyclic voltammetry? So there are four options. First, determine the electrode size. They provide the information about kinetics of electrochemical reaction, changes in the electrolyte concentration, and measures the pH of the solution. The scan rate affects the kinetic of the electrochemical reaction occur at the electrode surface. By varying the scan rate, researcher can gather information about the rate at which redox reaction take place. Faster scan rate may reveal kinetic limitation that are not evident in a slower rate. So based on the four options, option B shows the correct answer. Now moving to the next question. What is the primary focus of bioelectrochemistry? So there are four options. First, study of the metals and alloys, interaction between biological system and electrodes, thermodynamics of chemical reaction, optical properties of materials. So based on the if I differentiate this term bioelectrochemistry, so there are the two words that is present inside the terminology, that is biology and the second one is the electrochemistry. So electrochemistry is basically two parts in general. One is the electrode and another one is the electrolyte. So the primary focus, if I say the bioelectrochemistry, is the study that provides the interactions between the biological systems, basically in the cells, enzymes, biomolecule, and interaction of these biological systems along with the electrodes. Bioelectrochemistry explores the electrochemical processes that occurs within the living organisms or involve biological components interfaced with electrodes. This field brings together principles from both biology and electrochemistry to understand and manipulate the electrical behavior of biological entities. So there are 7 aspects. First is the electrochemical reaction in biological system, electrochemical sensors and biosensors, biofuel cells, Microbial fuel cells, electrochemical studies of biomolecule, bioelectrochemical processes in environmental monitoring, electrochemical studies of cells and organelles. So, if I differentiate it one by one, first one is the electrochemical reaction in biological system. So, there are various electrochemical reactions that are happen in the biological system. To understand those methods, we need to study the bioelectrochemistry. The second, electrochemical sensors and biosensors. So, the one of the major application of electrochemistry is that its application in sensing the pollutant or any other analyte. So, for that, for detecting the microbes or cells or certain enzymes, or we need to understand the bioelectrochemistry to making a sensor using the biological materials. Third is the biofuel cell. Biofuel cell basically help which can use the microbes for microbes like various from microbes or biomasses or any other material for the production of the fuel along in a eco-friendly way. So that is the biofuel cell. And the microbial fuel cell is a part of biofuel cell where we majorly use the microbe such as bacteria or microalgae or something. So that is the microbial fuel cell. Okay, so so we can say these two terms, biofuel cell or microbial cell or fuel cell, are somehow related to each other. So biofuel cell is basically any. So if I distinguish between two terms, biofuel cell and microbial fuel cell, biofuel cell uses the living organisms to produce electricity, which contains enzyme, microbes, cells, anything. But when it comes to microbial fuel cell, it basically involves the microbes, specifically bacteria or algae, etc. The fifth one is the electrochemical studies of biomolecule. So, electrochemical studies of biomolecule is also another very important factor. The electrochemical studies basically understood the electrochemical studies of biomolecule also helps to determine the sensors as well as to understand the various bioprocesses. The bioelectrochemical processes in environmental monitoring. That is, as mentioned earlier, it is similar to electrochemical sensors and biosensor. Electrochemical studies of cells and organelles to understand their fundamental setup inside the cell. In essence, bioelectrochemistry bridges the gap between the worlds of biology and electrochemistry. It offers a multidisciplinary approach to explore and apply the principle of both the fields. The knowledge gained from bioelectrochemical studies has diverse application ranging from medical diagnostics and healthcare to environmental monitoring and sustainable energy production. So, in a one sense, I can say this is biology. And so this is biology. Biology, and this is, suppose this is electrochemistry. and the overlapping area of these two is known as bioelectrochemistry. Okay, so now moving to the next question. So as per the what is the primary focus? Interaction, study of the metal and alloys, interaction between biological systems and electrodes, thermodynamics of chemical reaction, and optical property of material. The correct answer is interaction between biological systems and electrodes. Now moving to the next question. In bioelectrochemistry, what role do enzymes often play in electrochemical processes? There are four options: catalyst, electrolytes, insulators, and semiconductors. So bioelectrochemistry, enzymes often play a crucial role as catalysts in electrochemical processes. Enzymes are known as a biological molecule that act as a catalyst to facilitate and accelerate specific chemical reaction without being consumed in a process. Their ability to catalyze reaction under mild condition make them valuable component in bioelectrochemical systems. So as I mentioned earlier, so as I all know, the enzymes are basically known as the biocatalyst. So basically it facilitate or accelerate the specific chemical reaction without being consumed in the process. So the correct option is the catalyst. So so here it comes of the end of the session. So if I go back starting from end, so first we'll go to understand what are the electrode material surface preparation needed. The correct option is option D. All of there are four options: observing an electrochemical parameter such as heterogeneous electron transfer rate, observing an electrochemical parameter such as redox potential, observing an electrochemical parameter such as surface coverage, and all of the above. So the correct answer is all of the above. Now moving to the next question, that it despite its black color as a bulk sample, thin film of disordered graphic carbons are partially transparent in the far red wavelength range, partially transparent in the visible wavelength range, completely transparent, partially transparent in the UV wavelength range. So the correct answer is partially transparent in the visible wavelength range. Now moving to the option 3, following substrate are of key importance for most practical thin film devices. The correct option is there are four options: platinum, carbon, silicon or glasses, all of the above, and gold. So the correct answer is option D, all of the above and gold. Now moving to the question number 4. Cyclic voltammetry is an electrochemical technique which measures the current that develops in an electrochemical cell under condition where voltage is in excess of that predicted by the Nernst equation. The voltage that develop in an electrochemical cell under condition where the current is in excess of that predicted by the Nernst equation. The fourth, the voltage and current simultaneously measure the impedance of the system. So the correct answer is option A. The current that develops in an electrochemical systems under condition where voltage is in excess of that predicted by the Nernst equation. Now moving to the question number 5. Carbon electrodes are commonly used for, there are 4 options: metal production, energy storage and in batteries, and supercapacitor catalyst support. And the 4th option is all of the above 3 are correct. Choices are correct. So the correct option of this question is option D. All of the above 3 choices are correct. Now moving to the next question. What is the significance of varying the scan rate in cyclic voltammetry? So there are 4 options: determine the electrode size, provide information about the kinetics of electrochemical reaction, changes in the electrolyte concentration, measures the pH of the solution. So the correct option is option B, provide information about kinetics of electrochemical reaction. Now moving to the question number 7. What is the primary focus of bioelectrochemistry? So there are 4 options: study of metal and alloys, interaction between biological systems and electrodes, thermodynamics of chemical reaction, and optical property of materials. So the correct answer is option B, interaction between biological systems and electrode. Now moving to the question number 8, that is in bioelectrochemistry, what role do enzymes often play in electrochemical processes? There are 4 options: catalysts, electrolyte, insulators, and semiconductors, and the correct option is catalyst. So here comes the end of the session. I would like to thank everyone for joining me with today's session. Thank you everyone, and hope all of you to meet in the next session. Okay, so I increase one more here. Yeah, so they are basically densely packed wherever it is not very clearly pictured here, but they are usually densely packed. So now moving to the next one. So now this is the nucleus part, and there are certain particles who are roaming around this nucleus. They are known as a electrons. So these 2 are electrons, suppose. And okay, I am trying to give a more good picture of this. Yeah, okay, so they are basically, as I mentioned, and something like that. So as I mentioned, there are 3 types of particle. One is black particle, one is the red particle, okay, and another one is the blue particle. So the black particle, which is roaming around the nucleus, is basically the electrons, and the particles which is present in the nucleus are basically proton and neutron. So the electron usually carries the negative charge, the proton if I go by now, we go by the options. So the electrons is basically carries the negative charge, protons carries the positive charge. The third part is mentioned as ions. So what is ions? Suppose this is a particle which is contain 9 electrons, so it is unstable. So there is a property of an atom, like it try to get stabilized. So the stabilized means when there are equal number of protons and neutrons present in the, like in each orbit there are maximum 2 electrons are present. So and the maximum every atoms or every molecule, every atoms try to reach its inner state. So inner state means when it either present in 2 or in 8. So what happen in this case, ions, suppose there is a material which is contain 9, but it requires another 3 to get stabilized. So it take electron from the other particles, other molecules or atoms. So it contains a charge which is positive charge or negative charge. So this is known as the ions. And the fourth one is the neutrons. It does not contain any charge, but it plays a major role to enhance the mass of the atom. So neutron is the only particle here that does not hold a charge. Now moving to the next question. In a redox reaction, the chemical species that gives electron is called oxidizing agent or reducing agent. Suppose there are two material, one is X2 plus Y3 plus, and after the reaction we got X3 plus and Y2 plus. Okay, so there are two states, one is X2 plus. So in this case X2 plus, what happened to it? It donates one electron. Okay, I am trying to give you a more excuse me, I trying to give you a more better view. So this is X2 plus, it donates one electron, and because of that it converted into X3 plus. And in the case of Y3 plus, it receives one electron and convert it to Y2 plus. So what is the oxidizing substrate and the reducing substrate here? In a redox reaction, the chemical species that gives an electron is called as a reducing agent. So brief introduction, the reducing agent is the substance that undergoes oxidation, loss of electrons, thereby it reduces another substance. So it donates electron to another species. So in this case the X2 plus donates one electron, so it's become X3 plus. So this is the reducing agent. And oxidizing agent, the oxidizing agent is the substance that undergo reduction, gains an electrons and thereby oxidizes another substances. It accepts the electron from another species. In this case The Y3 plus accept one electron and convert it to Y2 plus. So this is the oxidizing agent. So in summary, in a very we can say the reducing agent is oxidized and the oxidizing agent is reduced. So the easy to remember this thing is Leo says Jigar. Loss of electrons is oxidation and gain of electrons is reduction, to help keep track of the terms of redox reaction. So now moving to the next question. In a redox reaction, the chemical species that accept electrons is known as oxidizing agent and reducing agent. So as I say, the chemical species that accept from the last example, we can say here's the material which accept electrons is known as a reducing the accept electrons is known as a oxidizing agent, because it help to reduce other. This help to oxidize others, and therefore it by yourself go for the reduction. So this is known as a oxidizing agent. So now moving to the next question, that is in a reaction where x3 plus and y3 plus is going to x2 plus y3 plus. As I mentioned earlier, we can say here x3 plus is losing an electron and become x2 plus is not balanced. So here so now the next plus is y2 plus okay. So x3 plus, it receives as electron and transferred into x2 plus, and y2 plus it's going to is going to donate that electron it's going to donate the electron, so it's become y3 plus. So in this case what happened, the x3 plus is gaining, so it is reduced, and the y2 plus is losing one electron, so it is getting oxidized. So you can solve in this way also. The initial oxidation state of x is plus 3 and the final oxidation state of x is plus 2. Whereas in the case of y, the initial oxidation state is plus 2 and the final is plus 3. So we can analyze that the x goes from plus 3 to plus 2. So basically the decrease of the oxidation state. So basically it is getting reduced, and y undergoes the increase of the oxidation state. So it's getting oxidized. So if I go for the oxidation state, if the oxidation state, suppose if the oxidation state is increased, so it means the oxidation occurs. So it's oxidation. If you remember this one, if the oxidation state is increased, this means oxidation. So obviously the opposite is the vice versa. When the oxidation state is reduced, they are getting reduced. So it will be help you solve by there itself without solving this one. So from plus 3 to plus 2, and this is for plus 2 to plus 3. So here is the correct answer. They are oxidized. So now moving to the next question. What amount of electrons are needed to generate 4.82425 coulomb of charge? Now there are four options. One is 1 millimole, one is 5 millimole, option C is 1 moles, and option D is 5 moles. So the correct answer. So for solving this question, we are using a formula which is given as Q equals to NF. So what is Q? U is the charge in coulombs, N is the number of electrons in moles, the amount of electrons in moles, the F is the Faraday constant, and the value of the Faraday constant is 96,485 coulomb per mole. So here the Q is also given, that is 482425 coulomb, and the Faraday constant is already known, so we need to modify this formula and we want to find the value of N. So N, after the reshuffling, we can get is as a N equals to Q by F. So the value is given as 482425 and 96,485. So the current value here is coming as 5 moles. Now moving to the next question. In a galvanic cell, oxidation occurs at anode. Cathode depends on the electron used or none of the above. So in a galvanic cell, oxidation occurs at anode. And is the quick explanation we are giving. So that is, this is the anode and cathode. Anode is where the oxidation takes place. It is the electrode where electrons are produced during a spontaneous redox reaction, and half cells at the anode involves the loss of electrons. Whereas in the cathode where the reduction takes place, it is the electrode where electrons are consumed during the spontaneous redox reaction. The half cells of the cathode involves the gain of electrode. In the summary, oxidation occurs at anode and reduction occurs at cathode. Okay, so the next question is the same in a different mode. In a galvanic cell, the reduction occurs at anode, cathode depends on the electrode and none of the above. So I am giving a more view. Suppose this is a setup of an electrochemical reduction. So there are two electrodes. This is anode. This is anode and this is cathode. So what happened here, the oxidation occurs. Because of that, we'll get the number of electrons generated which move from here to here and produce current, and after reaching here it getting reduced and help to deposit the metals or help reduce it and causes a depositions. So here the cathode where the reduction occurs. Now moving to the electrons in a galvanic cell, the electrons flow from anode to cathode. It is as in the previous picture we can see the electrons are started to flow from here to here. So the electron is flow from anode to cathode. So the anode and oxidation where take place, the electrons are released, and because of that electrons flow out of the anode. And the cathode where the reduction takes place, electrons are consumed and electrons flow into the cathode. Electrons flow from anode to cathode, and the direction of electron flow is opposite to the conventional current. So it is the current is generated from cathode to anode, flow from cathode to anode. The same question, in a galvanic cell where the conventional current flows from oxidizing agent to reducing agent, the oxidizing agent is basically, so here is the question a different tricky way. So here they are telling the galvanic current, the current flow from oxidizing agent to reducing agent to oxidizing agent, and depends on the electron. So I again draw this. Okay, so there are two cells. Two electrodes. Suppose this is anode, this is cathode, and here it is immersed in okay. So this is anode, this is cathode, and this one is electrolyte. This is electrolyte. So this is the basic structure of a galvanic cell. So what happened in the anode? There, if we go for the anode, what happened? There is a loss of electron. So what happens? Suppose it's A, it lost the electron and it's become A plus. And what happened in the cathode? It's it gains electron. So what happened? C plus E, so it's become C minus. So there are two forms. So if I say this way, so here it's happening the oxidation and here is happening the reduction. So but if it is happening the oxidation, this means it is reduced and this is oxidized. So basically it is the opposite of the process. So this means A is reduced and C is oxidized. A is the reducing agent and C is the oxidizing agent. So what happened? The electron is transferred from oxidizing agent to reducing agent. So the current is so if the electrons are flow in this direction, the flow of electron, so the current is flowing opposite direction. So what happened? This means it's help to reduce the electron is flow from reducing agent to oxidizing agent. So what happened? The current is flow from oxidizing agent to reducing agent. So here is the option. A conventional flow from the oxidizing agent to the reducing agent. So the oxidizing agent is the species that undergo reduction. So in this case, this is the species that undergo reduction. So here, what happened in the case of C, it's undergo reduction. So this is the oxidizing agent. And what happened in the case of A, it is undergo oxidation. So it doesn't mean it's a reducing agent. So the current is flow from C to A, means its current is flow from the oxidizing agent to the reducing agent. So if I get no details, oxidizing agent, I say the conventional current is defined the flow of positive charge in a galvanic cell. The positive ions or the cations are moved from the anode to the cathode through the external circuit. The movement of positive charge is a direction from the oxidizing agent to the reducing agent. So this current is transferred from the oxidizing agent to the reducing agent. Now moving to the next question. For a reaction to be spontaneous, delta G is positive, delta G is negative. Delta G is unrelated to the spontaneity of the reaction, and delta G is always 0 for all chemical reaction. Okay, so I want to give you a brief about what is the spontaneity of the reaction. If I go for an electrochemistry perspective, the spontaneous redox reaction is generates the voltage itself, whereas in the non-spontaneous redox reaction occurs when an external voltage supply is given. So basically, it's generated the voltage or potential difference due to the difference in the electrons. So basically, this is the spontaneous reaction. And the spontaneous reaction, what is this D and G term? So delta G is basically the also known as the Gibbs free energy. This is known as the Gibbs free energy. So what is the Gibbs free energy? So it is, what is the Gibbs free energy? So the Gibbs free energy is a thermodynamic potential that can be used to calculate the maximum amount of work other than the pressure and other than the pressure volume work that may be performed by a thermodynamically closed system at a constant temperature and pressure. So there is a formula, that is del H or enthalpy equals to del G plus T delta S. So as I know, the H is the enthalpy, is a change in delta H is the change in enthalpy, delta G is the change in Gibbs free energy, and delta S is the change in entropy. So from here, if I want, there are two terminology. One is the del G if positive. As per the option, one is del G is greater than 0. The next one is del G is less than 0, and the third force del G equals to 0. So the for a reaction to be spontaneous, the del G must be negative. So if we give a small of these three conditions, when the del G is less than 0, the reaction is spontaneous and favors the formation of the products. Where the del G is greater than 0, the reaction is non-spontaneous and its formation of the product is not favored. And while the del G equals to 0, it means the reaction is reversible. So here in this case, the del G should be, the reaction to be spontaneous, the del G need to be less than 0. Now moving to the next one, which of the following is a property of a salt bridge? So it is a gaseous in nature, it is in liquid in nature, does not affect the overall cell reaction, and it does not contain in any ion. So can you tell me what is this salt bridge? Salt bridge is a device which is used in an electrochemical cell for connecting its oxidation and reduction half cells wherein a weak electrolyte is used. It is basically a U-shaped. Okay, so it's basically, if I give you a very photograph of this, suppose there are weak electrolyte. Suppose here is the electrolyte is, okay, it is ZnSO4, and here the electrolyte is CuSO. Here it is mentioned as CuSO4. So here suppose the electron is immersed in ZnSO4 aqueous solution. So here the electrode is zinc, and they are not compatible for the same solution. Suppose we are getting, so here the electrode is Cu. So and they are connected through externally, and there will be a U-shaped material which is attached to both the which will connect both these half cells, is known as the salt bridge. So here suppose the salt bridge is KCl. A salt bridge basically a U-shaped tube filled with concentrated electrolyte solution, often a salt solution. This liquid state allows ions to flow from between the half cells and completing the electric circuit and maintain the charge neutrality. The salt bridge plays a major crucial role in balancing the charges during an electrochemical reaction in a galvanic cell or in an electrolyte cell. So the correct option is, it is in the liquid state. Now moving to the next question. At all point the migration of charged species into the salt bridge is dash the migration of the charged species out of the salt. So the correct answer is in the equilibrium with the migrated charged species out of the salt. If a salt in a salt bridge, the ions move from the salt bridge into the half cells to maintain the charge neutrality. The migration of the ions is bidirectional and it occurs until the electrochemical on both of the sides reach equilibrium. Once the equilibriums are reached, the flow of the ions into and out of the salt bridge is balanced, but there is no net migration of charges between the salt bridges, and the half cells between the salt bridges and the half cells, and this ensure the electrochemical reaction in the cell process smoothly without building up the charge that could impede the reaction. So the correct option here is at equilibrium with. Now moving to the next question. What is for she, which of the following is true? The concentration of H plus equals to 0.1, H plus equals to 1, and the OH minus equals to 0.1 and OH minus equals to 1. So what is she? She is basically known as the standard hydrogen electrode. So as I say, she is known as standard hydrogen electrode. So it's a standard, it is a redox electrode which forms the basis of the thermodynamic scale of the oxidation reduction potential. The value of the standard electrode potential is 0, which forms the basis for one need to calculate the cell potential using different electrode and different concentration. So now the question, why hydrogen is the chosen for this electrode? So because hydrogen is the first element in the periodic table, at it is so we can consider it as a number 1. So in this case, the standard hydrogen electron, the condition defined with respect to the concentration of protons. Here the standard hydrogen standard condition for She is H plus, concentration of H plus is considered as 1 mole per liter. The correct answer is the H plus equals to 1. Now moving to the next question. Which of the following electron is used in standard hydrogen electrode? So here there are 4 options. One is copper, aluminium, tungsten and platinum. The electrode used for the standard hydrogen electrode half cell is typically made from platinum. Platinum is chosen for its inert nature and ability to catalyze the half reaction involving hydrogen ions. The half reaction of the hydrogen electrode would be 2H plus 2E minus, that is comes as hydrogen gas. The platinum serves as a suitable and inert condition for the correct answer is the platinum. Now moving to the 5th question. Which of the following is the best reducing agent? Fluorine, ozone, silver and lithium. So the correct answer is lithium. So as I say, the reducing agent is especially oxidized. So what means by oxidized? It means the readily lose electron. So there are 3. One is the so it's like the lithium. If I go for the periodic table, the first one comes as hydrogen. It contains 1 electron. The next one is the helium, which is an inert gas, and third one is the lithium. So as I mentioned, in all the cases, the electrons present in the orbit try to be stabilized or try to get its nearby inner structure. So what happened? Because of that, lithium, which contains the 3 electrons, are always ready to donate 1 electrons and become stabilized. So because of that, lithium has a strong tendency to donate electrons and undergo the process of oxidation. So in a redox reaction, it is a strong reducing agent that can easily give up the electrons, and lithium has a high reactivity in this context. So the correct answer here is lithium. Now moving to the next question. In a fuel cell, which statement is correct? So if I go for a fuel cell design, so can anyone tell me what is a fuel cell look like? Any idea about that? So okay, I'll draw a video about the fuel cell. So okay, so there are first okay. So if I go for a basic structure of a fuel cell, here there are two electrode and the electrolyte is sandwiched between them. So this is the basic structure of this electrolyte. So here what happens? They are connected through a circuit, external circuit. So suppose this we considered as anode. This one is considered as a electrolyte, and this one is considered as a cathode. So what happened in like in a fuel cell? Suppose here in this case the fuel is supplied here in the anode surface. What happened? The hydrogen gas, suppose here the hydrogen gas or fuel is applied. So what happened? This H2 reach to the surface of the anode, and what happened in the anode happened basically the oxidation reaction. So oxidation reaction means it lose a electron, so it's become H plus, and suppose here is H plus which is present in the electrolyte and transferred to the cathode, and this cathode it reaches the cathode, whereas in the other side simultaneously in the cathode side we add air which contains the oxygen, and after reaching this cathode it becomes O2 minus. After receiving the electrons it's become O2 minus, and these the two H plus and O2 minus when they join together and produces the steam, and this steam is coming as this side along with the unreacted gases. So this is, and because of that the electrons are transferred from this anode to this cathode and electron current are generated. So basically in this process we can produce electricity from any fuel, any fuel. So here in this case so it helps to produce this suppose different type of fuel cells plays a different role. So it is what is the fuel cell? So fuel cell is an electrochemical cell that converts the chemical energy of a fuel and an oxidizing agent in an electricity through a pair of redox reaction. So in the case of fuel cell, which statements are true? The first is it is a static compartment. Reactants are fixed and filled at the start. Phase reactants flow past the electrode in a dynamic setting. Products are not removed from the cell compartment. The correct answer, as you can see from the here, they are the always the unreacted gas are after reaching to the electrode, they are coming out from the outlet, whereas in this case the air which is supplied to the cathode is also coming out from the outlet. So there is always a phase reactant flow past the electrode in a dynamic setting. So basically in a fuel cell, reactant which is typically a oxidant or a fuel continuously flow into the cell, react electrochemically with the electrode, specifically in this case we can say it's anode, so and produce the electricity. The reactant are not fixed and filled at the start. Instead, they are continuously supplied to the cell. This dynamic flow of fresh reactant distinguishes the fluid, like the fuel cell, from the static system and allows for a continuous production of electrical energy as long as the